It claims that it can hear me. I can see that it can see me. So unless we run out of memory, we should be fine. Good. For the benefit of those who either don't remember everything we did in the first chunk of this course, which was supposed to be the only chunk of this course, or for those who are new here and never saw it the first time, we spent a few lectures reviewing the phenomenology of superfluidity as a preparation to superconductivity and to see what was the same and what was different. We then went on to superconductivity. We talked about the phenomenology of superconductivity, and then we started to get into theories. First, the Landau-Ginzburg theory, which is a long wavelength theory of what the superconducting order parameter does, how it responds to walls and so on, how it makes vortices. And then in the last 3 lectures, we started developing the Bardeen-Cooper-Schrieffer theory of how that all comes about microscopically, how the electrons attract each other to form pairs, and how those pairs condense, or in what sense those pairs condense. So let me very briefly restate some key things, particularly from the last couple of lectures that we're going to build on today as we go on to think about excitations of the superconducting state. So obviously, I should emphasize, particularly as there are new people here, this lecture series thrives on discussion with the audience. So please do be discussing all the time. Feel free to interrupt with any questions, points of interpretation, things you think are wrong. This is absolutely fine, and there is no quote on these things. But Andy will show you the way. So far, we did some macroscopic phenomenology of superconductors. So obviously, as per the name, that included perfect conduction, also perfect diamagnetism, or the Meissner effects. And we also mentioned, as a contrast with the superfluid case, that there is a fully gapped specific heat. That is to say that the specific heat capacity at low temperatures shows an activated behavior as for a system with a gap in its energy spectrum. One of the things we have yet to explain is where that gap comes from, but hopefully we'll get to that today. We then formulated Ginzburg-Landau theory, which is written in terms of some assumed complex order parameter for the superconductor psi, which depends on where we are in the sample and can vary slowly in space. And we developed that basically by writing down the theory that we'd used for a superfluid and then coupling it to the magnetic field via the usual sort of momentum goes to momentum minus vector potential trick. But that led to some important realizations, which is that the U1 phase rotation symmetry that we had in the superfluid theory and that we broke to make the superfluid state becomes a gauge symmetry in the superconducting theory, and you can't break gauge symmetries because they're just redundancies in description. So we had some discussion of the fact that that already meant that the superconductor was going to be quite different from the superfluid in its properties in some ways, and it's that coupling to the electromagnetic field that makes all the difference. You might think, well, I can just turn the charge of the electron off and go smoothly from the superconductor to the superfluid, but you can't, actually. That limit is singular. So we discussed that. Sorry?
That limit is
singular. So yeah, so Anderson points this out in the 62 paper, that there are formulas that have the electron charge in the denominator. So you can't just take it to 0 and say everything goes the same. So they really are different, superconductors and superfluids. And yeah, we had some discussion of the fact that the transition should be thought of as condensation, not, as people often say, breaking of gauge symmetry. And we talked about type 1 versus type 2 superconductors, which was basically a discussion of the coherence length, which is the length scale on which the order parameter recovers if you perturb it, versus the penetration depth. which is the distance that magnetic field gets into the sample from the edge. And those are both length scales that characterize the superconductor. There's no particular reason why one should be bigger than the other. So in type 1 superconductors, the coherence length is larger than the penetration depth, and so it's never worth making vortices. You just go normal. Whereas in type 2, the penetration depth is larger than the coherence length, so it's worth making vortices, and there's a vortex phase in a magnetic field before you go. Not you personally, of course. And then in the last 3 lectures, we started looking at BCS theory, and that has 3 key components: electron-electron attraction by virtual phonon exchange. So phonons are not stronger than Coulomb repulsion, but they hang around for longer, and it turns out that's enough, so that at low frequencies you get a net attraction between the electrons. We wrote a BCS Hamiltonian, which has a cartoon version of that attraction in it. We showed, following Cooper, that in the presence of a Fermi surface, an arbitrarily weak attraction produces bound states, even in 3 dimensions, which would not be the case in vacuum. Right? So that's another important ingredient. A weak attraction plus the Fermi surface means that you can bind 2 electrons into a bound state. And then we followed Bardeen, Cooper, and Schrieffer in basically guessing a variational ground state based on this Cooper pair formation for the many electron case. And it really is a guess. So I've chosen in this course not to try and pretend it isn't. We just sort of write it down, work with it, and see what happens. But it's, of course, an informed guess. So that state is the product over all K states of some amplitude for the K state being empty and some amplitude for it being occupied by a Cooper pair. And we have chosen to make the Cooper pairs out of equal and opposite momenta and spin up and spin down. So this is a spin singlet Cooper pair. We will assume that these V's and U's actually only depend on the modulus of K, which means that the thing is isotropic in K space. So this is a singlet S-wave superconductor. We'll talk in the next few lectures about what might happen instead. But actually in the BCS Hamiltonian that we wrote down, where we just have a constant attraction between electrons, basically independent of momentum transfer, this is the only thing that can happen. Notice that this 0, which I emphasized before, is not the filled Fermi sea. It is the true vacuum of the electrons. So we don't build this state by perturbing the Fermi sea. We build it by starting with absolutely nothing. And we pointed out that depending on your choices of these U's and V's, this state actually includes the filled Fermi surface. If you make V1 up to Kf and 0 above it, and U0 up to Kf and 1 above it, this just gives you a regular filled Fermi sea. So the BCS state, the family of BCS states, includes the filled Fermi sea as one of its possibilities.
But then it's a non-superconducting state.
That would not be superconducting, certainly, but you can have non-superconducting states in this representation too. There's a normalization requirement. Which is that for every K pair of the square of the sum of the squares of these amplitudes should be 1. Right? So all we're really saying in this state is that if the electron at K with spin up does something, the electron at minus K with spin down has to do it too. We're not allowing those things to break, but they can reconfigure as long as they remain Cooper pairs. And then we just sort of mechanically minimized the energy of the state, expectation value for Hamiltonian, with respect to all of these parameters. This is all in the notes for lecture 10. It's important that we did that for a fixed number of electrons, which got a chemical potential into the problem. And without writing all the expressions again, I'll just draw the graph of what we derived. So as a function of mod K, this is Kf, where the original jump in occupation would have been. And what one finds is that, so this is mod Vk squared, the probability of being occupied by a Cooper pair. And this is mod UK squared, the probability of the state being empty. These things would have been sharp steps in the metal, and now they're smeared out over some range in momentum. And this is not a thermal effect, right? This is a ground state calculation. This is the system deliberately deciding to fuzz out the Fermi surface in order to take advantage of the pairing interaction. And the pairing interaction can only operate on states where both of these U's and V's are non-zero. So in some sense, what the pairing interaction does is to give you an energetic benefit for fluctuating between a state with a Cooper pair and a state without one. And so it does that in some vicinity of the Fermi surface. But obviously then deep in the Fermi sea, that becomes too expensive.
And did you, I missed your lecture, but did you give any statement of the kind of Pippard argument for what that range of K was going to be?
Yeah, well, I sort of, I don't know whether it's exactly Pippard's argument, but I said that this was mod delta over h bar Vf, where Vf is the Fermi velocity of the parent metal, and delta is a parameter that sort of emerged in the solution of the variational problem. Let me state it because it's important. So it was the sum over Q states, the strength of the interaction, G times V star U. At least in my notes, different sets of notes would have called that delta star. Some people don't include the G. There's actually some variation. I like to have delta be an energy, so I can put it in expressions like this. And so this illustrates the point that I made, that the superconducting order parameter, which tells you how much of this fuzzing out you get, is basically you just go around all the K states and you tot up which ones of them are participating in this fluctuation between empty and doubly occupied. And that just gives you the superconducting order parameter. Was that what you had in mind?
Yeah, I mean, I just found it pretty cool that in the early 50s, when the heat capacity came out, and they realized there had to be something like delta, right, from the heat capacity, Pippard, it's dimensional analysis in some way, but I don't think it was so fashionable in those days, very intuitive thing to do, that he'd already stated that the successful theory was going to involve some perturbation to the electronic system on that range of K.
Yeah, and I mean, Bardeen, Cooper and Schrieffer in their 57 paper very much lean on that.
Yeah.
So they just have a paragraph at the end that says, it seems very likely that this is going to produce a gap. And as is already known, that would account for the Meissner effect and these other phenomena. Yeah, exactly. So there's a 55 paper also from Bardeen saying that if you have a gap, you'll have a Meissner effect. Yeah, so they knew the links between lots of these things, but it was just a question of, you know, how do we really run that
Absolutely. Not a totally trivial step.
No, indeed, indeed. Okay, so that's the picture that we get. And I just want to emphasize one other thing. So at the moment, we've got that the U's and V's are functions of delta, and the delta is a function of the U's and V's, which feels a bit circular. But actually, in the course of minimizing the energy, we proved that a solution exists only if the following self-consistency equation is satisfied, which is that the sum over k states of this mysterious square root that appeared in the calculation, which we will understand better by the end of today, I hope. So this is the BCS gap equation. Because it determines mod delta. And we solved it in the case of weak coupling to discover that mod delta was twice the divide frequency of the phonons that are causing the pairing times e to the minus 1 over density of states at the Fermi level of the parent metal times coupling strength. And importantly, this is much weaker, right? At weak coupling, this denominator is small, so this fraction is big. So you've got an exponential a long way to the right of the graph. So this number here is much less than 1, which explains why the gap that they were seeing in experiment was so small. Yeah, it corresponds to a few Kelvin, whereas the Debye temperature is a few hundred Kelvin. So an important success of this theory is that it explains why the energy scales associated with the superconducting state are so much lower than the energy scales associated with the interactions that cause the superconducting state. You might wonder, how did the Debye energy get into it? But it's hiding in this little prime. So to remind you, or tell you if you didn't know it before, in the definition of the BCS Hamiltonian, we cartoon the effective attraction due to the phonons by saying it exists only within a window of the Fermi energy, which is given by the Debye frequency. Right? Above that, the Coulomb repulsion starts to kick in, and you no longer have the attraction. That's a complicated functional form, but we're just pretending that the attraction is minus G if we're within this energy of the Fermi level and 0 otherwise. Right? And so that scale turns up in the calculations because it's the upper limit on the integral that corresponds to this sum. Good. And so this delta is a natural choice for the superconducting order parameter. I mean, in one trivial way, in that it's, if we set it to 0, we get back to the ordinary metal. So it's measuring how much superconductivity we have, how much disturbance in the distribution functions we've got relative to the ordinary metal. And let me just make a couple of notes about it. It's complex because UK and VK are complex. And that's good, right? We figured out from our Landau-Ginzburg theory that we were looking for a complex order parameter, so maybe this is a good candidate. And we can also ask from the definition, what do we require to have a non-zero value of this order parameter? It means that we have to have non-zero U and V for the same K. So the metal has U equals 0 below the Fermi level and V equals 0 above it. So this order parameter is always 0. We have to have some region in K-space where both U and V are non-zero, and the size of that region basically determines the order parameter. But also, the relative phase of UK and VK must be the same for all of the K points that are involved. That's a slight exaggeration. It could vary slowly, but if I had a random phase relationship between these things, then when I summed over all the K points, it would average to 0. Right? So an important feature of the superconducting state is that I have U and V are complex numbers, so they have a relative phase. That relative phase has to match, basically, for all the states that are involved in the superconductivity. And if it doesn't, then the energetic gain that you get from having it cancels out. And so this sort of phase locking is in some sense, it's called phase stiffness, is in some sense the real essence of the superconducting state. There is an energetic advantage to phase locking all of these fluctuating Cooper pair points together. Okay. I've got a little bit more to say about that because we can actually also show quite easily that this order parameter is charged 2e, which will explain another feature of the Landau-Ginzburg theory that we just had to put in on phenomenological grounds. But as we've reached a board cleaning moment, maybe it's a good point to ask if there are any questions. Yeah.
So does this mean that this theory only holds for Fermi surfaces which are deflection symmetric, because we're assuming if there is a state at A, then there should also be a state for -3?
Yeah, I mean, that's a great question to ask, particularly in this institute, because the Fulda-Ferrell-Larkinov-Chinnikov phase is one of the phases you can get into if that condition isn't satisfied. So yeah, we have so far assumed a completely isotropic Fermi surface. And obviously you can ask what happens if the Fermi surface isn't isotropic, and what if it breaks inversion symmetry so that the existence of a point at K doesn't mean a point at -K. What if time reversal is broken? You put the system in a field, then you have opposite K points, but the spins are both up, so you can't make a single Cooper pair of this form. We'll talk a lot about that in the coming lectures and what alternative order parameters might develop. So yeah, it's the simplest rule is that you generally want to pair time-reversed states to get conventional BCS-type superconductivity. That rule can still work even if K is not a good quantum number at all. So even in quite strongly disordered systems, you can get superconductivity at low temperatures. And in those cases, you're usually still pairing time-reversed states, even though they're no longer labeled by a momentum, they have some localized wave functions and so on. But that can still be enough to run a supercurrent by tunneling, basically. Yeah, so no, quite right. Here we're assuming a completely isotropic Fermi surface. So and we haven't broken time reversal, we haven't applied a magnetic field. So I'm guaranteed that there are degenerate single particle states, K up and -K down. Yeah.
And, just from the experimental point of view, it's amazing that, when he said a disordered superconductor, even completely amorphous materials often support superconductivity with very similar TCs to the TCs of their crystalline counterparts. So this is all nice in its physicist language, but what you were saying is really important. And these days there are all of these what are they called? Some, massive entropy alloys, right? Where these alloys of 10 different elements, as disordered as you can be, 15, 20 Kelvin superconducting transition temperatures. It's unbelievable.
Yeah.
Right. So this is a sanitized physicist subset of what is required to get superconductivity.
Yeah, absolutely. And I guess the fundamental thermodynamics of that is nature loves a full gap. Right? I mean, I remember Alexei pointing this out to me when I was a graduate student, and I've thought about it many times since. Right? If you think about basically what would the system like to do as you cool it down? Well, if it's got some occupied states and some empty states, it's always a good idea to push the occupied states down and the empty states up. By pushing the occupied states down, you lower the total energy. By pushing the empty states up, you lose nothing. So opening a gap is generically energetically favorable, and the fuller the gap, the better. Good. Other questions? Yeah.
Maybe somewhat related to the previous comments. So when people say this is a BCS-like superconductor, what particular aspects of the sanitized theory are they talking about?
I'm so glad you asked. There is no agreement on the use of the phrase BCS-like or non-BCS-like. People sometimes, possibly for publicity reasons, call things non-BCS-like if they violate even small features of this approach. So some people say that the superconductor is non-BCS-like when, even though its S-wave has a full gap, obeys the Landau-Ginzburg theory and so on, the pairing didn't come from phonon exchange. Sometimes people call it non-BCS-like if the pairing is not S-wave, so if these U's and V's are not isotropic in K, even though actually BCS in their original paper didn't commit themselves to the fact that they would be. So yeah, and any deviation is used in some corners for calling it non-BCS. The Landau-Ginzburg theory is quite robust, and it's finding superconductors that don't qualitatively follow the Landau-Ginzburg predictions, I would say, is more or less impossible, because they're really just based on symmetry and a little bit of input from renormalization. But then, yeah, when you start asking about how the superconducting state formed and why it beat other states, then people see differences. So, for example, in a BCS superconductor, if you ask about the kinetic energy of the original electrons versus the potential energy, which you can easily calculate, when the superconducting state forms, the kinetic energy goes up because you messed with the Fermi surface, but the potential energy goes down because it's taking advantage of the pair. And people refer to those as potential energy-driven superconductors. Dirk van der Marel and others have made much of the fact that the underdoped cuprates seem to be the other way round. When you go into the underdoped superconducting state in the cuprates, the potential energy goes up, but the kinetic energy goes down. That, I would say, is actually quite non-BCS-like, and I don't think it's understood why that happens. Curiously, as you go to the overdoped side, it switches back to the normal behavior. So, yeah, there is no agreed use of these terms.
First comment, I think the confidence that one can have in the experiment that is claiming that is pretty limited. I mean, you know, that's optical conductivity. There's a huge subtraction that goes on there. You're looking at the absolute tail of a signal. And, you know, Van der Marel's clear about that. Then he tells us, but I know how to do it. Maybe, maybe not. The other thing is about BCS, non-BCS. Here you do require you have a high density, right? Because you have a Fermi surface the way you're thinking, and that means that you probably discussed this. As you go superconducting, millions of electrons go superconducting. They pair and superconduct immediately, right? So if you think about, you can always think about a coherence volume, which would be the coherence length cubed. Within coherence volume of in a BCS calculation, you're inevitably going to have millions of electrons. I think that's very hard to get around the whole way this is done. And there are some circumstances where observed superconductors, like the cuprates, only have 1 to 10 electrons in that coherence volume. So that's another thing which is used to say that it's non-BCS-like, but that's saying it's closer to BEC-like than BCS-like. And that's coming up a lot in atomic physics.
Yeah. Yeah, no, it's well worth mentioning the BCS-BEC crossover. Because here the coherence length is huge compared to the interparticle spacing. So you shouldn't think of these Cooper pairs as little bosonic objects that then condensed. We're not in that limit at all, which is why we're having to write a wave function, which is so different from what you would write for a Bose-Einstein condensate. But clearly, if I crank up the attraction between the fermions, eventually the two fermion bound states will become tiny compared to their mutual spacing. And then I've basically bound the fermions into real space bosonic bound states, which then condense just like a BEC. And actually, let me just say something about this, because I didn't have anything so far on BCS BEC. So if I think about what that means for the phase diagram of temperature versus the strength of the attraction. So we've done our calculation down here, and we get a critical temperature that rises from 0. I mean, I am optimistically assuming that the critical temperature will behave the same way as the superconducting order parameter, but it seems likely that it does, right? So the superconducting order parameter grows from 0 in this exponential way at weak attractions. And then the question is, what happens when the attraction is stronger? And then you can easily argue that there must be 2 scales in that case, right? So if I have an attraction of strength G and it is the largest scale in the problem, it will typically make molecules with a binding energy of order G. So there must be some scale here where the electrons form into dielectronic molecules. But then those condense. And the BEC condensation temperature is inversely proportional to the mass of the molecule, i.e. inversely proportional to that binding energy. So it must again go to 0 as the molecules get more strongly bound. So the argument is that we must have a situation like this, where at weak coupling, as you say, the pairing and the condensation are simultaneous. At strong coupling, the pairing scale goes up with increasing attraction, and the coherence scale actually goes down. And one of the early suggestions for the cuprates is that the pseudo-gap regime that you see might be this regime here, where you've started to form the pairs, but you haven't got down to the temperature where they cohere. There are problems with that argument, like how does the superconducting dome manage to stick out beyond the T star line? But anyway, it's an early suggestion of what might be going on. Good. Other questions? Sonia.
So I was wondering for the gap is complex. So how could you, for example, experimentally extract the phase?
Very good question. Some of the stuff that we discussed in the first part is relevant to that. So, for example, we talked about the Josephson effect that you see when you put 2 superconductors with different phases on either side of an insulating junction, and the current is related to the phase difference. So you cannot experimentally extract the absolute phase because there is no meaning to the absolute phase. It's a gauge. It's not a gauge invariant quantity. So depending on what gauge you picked for your magnetic field, that phase will be a different number. And notice that the BCS theory does not tell you anything about what it should be. It predicts the modulus of delta, and it leaves the phase completely free. That's because only the modulus of delta is a gauge invariant quantity, so only it can affect the energy. However, phase differences and phase gradients are perfectly well defined, right? In just the same way that the electric potential changes when you change the gauge, but the electric field, which is its gradient, doesn't. So you can measure phase differences between different superconducting samples using things like the Josephson effect, but the absolute phase has no meaning.
But when we come on to unconventional order parameters, there are experiments you can do to tell that the phase change sign around the Fermi.
Absolutely, which is also a phase difference measurement,
Yeah,
but just in case space. Yeah, indeed. Yeah, that's right. So phase differences between the order parameter for different Ks, right? I mean, you can sort of see that although here we've defined this order parameter summing over all K states, I could clearly just drop the sum and say that this product of V star and U is some kind of superconducting order parameter that's local in K space. And then I could ask, can it take different values in different bits of K space? Can its phase change in different bits of K space? Are there ever energetic reasons why that would happen? And that's exactly what we'll be talking about in unconventional order parameter symmetries. Good. Any more for any more? Great. We should clean the boards. It is conventional to have a poem or a song at this time. Shall we have? Did I do sonnet number 60 last time? Shakespeare, that is. Only one person gets their sonnets numbered. Okay, well, here's something about the passage of time. Like as the waves make towards the pebbled shore, so do our minutes hasten to their end, each changing place with that which goes before, in sequent toil all forwards do contend. Nativity once in the main of light crawls to maturity, wherewith being crowned crooked eclipses gainst his glory fight, and time that gave doth now her gift confound. Time doth transfix the flourish set on youth, and delves the parallels in beauty's brow, feeds on the rarity of nature's truth, and nothing stands but for his scythe to mow. And yet, in times of hope, my verse shall stand, praising thy worth despite his cruel hand. Oh. Please, no need. Good. So let me say one more thing about these phases. Because an unexplained feature of the Landau-Ginzburg theory is that the order parameter had charge 2e, we can already sort of see that because this theory was built out of Cooper pairs, it's natural that there should be a charge 2e, but we can actually show directly that this delta has charge 2e. And so that's sort of the last piece in identifying delta as the order parameter that we wrote down in the Landau-Ginzburg theory. So yeah, so if I make a gauge transformation, that involves rephasing my fields so that all the C daggers get multiplied by a complex, unimodular complex number e to the I chi. And so the U won't change when I do that because it doesn't have any C daggers attached to it, but the V will change. And the V will pick up e to the 2 I chi because it's attached to a pair of electron operators. And so delta, because it's a product of V and U doesn't change. V picks up e to the 2 I chi, so V star picks up to the minus 2 I chi. So this order parameter rephases under gauge transformations in this way. And so we can read off immediately that it is a charge 2 object. In some sense, the definition of the charge is what sits here when a gauge transformation happens. So if you were happy already saying, well, it's obviously charge 2 because it's got to do with Cooper pairs, fine. But actually, I'd say more rigorously, this delta is charge 2 because under gauge transformations, this is how it transforms. And so these things taken together strongly suggest that this complex order parameter that we were writing in the Landau-Ginzburg theory is just this delta from the BCS theory, where we've slightly promoted it to allow it to vary slowly in space. This is the kind of thing we actually always do, right? I mean, we define temperature for an isolated box of gas, but then when we talk about our bath water, we say that the temperature over here is a bit higher than the temperature over here. We define the Fermi energy for a single large sample of metal, but then we say that the Fermi energy in this place in the MOSFET is different from the Fermi energy in this place. So we're doing the same kind of trick here. We're starting with a reference theory where the superconducting order parameter takes a constant value. We show that order parameter is charge 2e, and then we ask, okay, what would the theory be for very slow spatial variations of that order parameter? And we can sort of construct that on symmetry principles as Landau and Ginzburg did without having to resolve the BCS theory every time. You don't have to resolve the kinetic theory for the exact water in your bath to talk about the temperature varying from here to here. That's described by a sort of hydrodynamic theory, which is built on top of the microscopic one.
Nevertheless, didn't Gorkov do some big heroic effort to show that BCS turned into Ginsburg-Landau?
So you can do it.
Yeah.
But I mean, yes, and it was big and heroic.
Yeah.
I think many people were kind of happy with this argument. But if you weren't, then obviously if you think it's important to show that you really can, out of the microscopics with slow variations, get Landau-Ginzburg, then that can be shown.
That probably was important to them about 1960, right, when they were grappling with the new microscopic theory.
Yeah, maybe. Good. So that's hopefully tied together some of the different pieces of the first section of the course on superconductivity. And so now you can still do your Ginzburg-Landau theory. It's still the most efficient way of describing vortices, superconductors in proximity to walls, type 1 and type 2, and so on. It's just that now we have a microscopic underpinning for what the meaning of this complex order parameter is. It's really the local value of this delta, which is the local extent to which the superconductor has smeared out the Fermi surface in order to benefit energetically from these Cooper pair fluctuations. And all of the discussion we had in the case of the Landau-Ginzburg theory about which phases are physically meaningful and which aren't also applies here. The absolute phase of delta is not meaningful because it's not gauge invariant, but any differences in phases of delta from one place in real space to another, or one place in K space to another, are meaningful and are in principle measurable. Good. So as far as long wavelength properties of superconductors go, we're kind of fine. But of course, that's not the only kind of experiment you can do. So the next question I want to ask is, what about non-long wavelengths? Probes. For example, and this was an important example in the early days of superconductivity, and it's still an important example now, tunneling. Suppose I make a point contact to my superconductor and I change the voltage bias and I try and push electrons into it or pull electrons out. That's not describable purely in terms of what the delta field is doing on long wavelengths because it's a local probe. So can the BCS theory tell us something about what we expect in those cases? And the answer is yes, it can. So this is really the last thing I want to talk about in terms of purely conventional BCS, isotropic, S-wave superconductivity, but I think it's important to talk about the predictions for the single particle excitations of the superconducting state. So presumably, this excites the BCS state. So really the question we're asking is, what are its excitations? So the excitations of the ordinary metal were quasi-particle, quasi-hole pairs, or individual quasi-particles, if you're tunneling stuff in from outside. What happens if we tunnel stuff into a BCS superconductor? And how do we work that out? So here I'm going to deviate from James's book. I have generally been following the line that James Annette's book takes on these questions, but I don't like the way he does this. So I've invented a way. And so, take it for what it's worth, but I think this is easier to follow than the way these things are normally presented. And it also does not involve you in quite so much navel gazing about negative energy solutions, blah, blah, blah. So, so in this way, there will not be any negative energy solutions. The BCS ground state is the ground state. Excitations will always have positive energy, and we're just going to talk about what they look like. So the principle is that excitations must have operators that create them. So without knowing anything about them, we can call those operators B dagger. And they will have conjugates. And so the conjugate of B dagger must annihilate an excitation. The ground state has no excitations. So B on the ground state, these are operators, I'm not being very careful with my hats. So B on the ground state must be 0. So we can turn that logic round. If we can find an operator that annihilates the ground state, it must be the annihilation operator for some excitation. And by taking its Hermitian conjugate, we then have the operator that creates that excitation, and we can ask about its properties. Now, of course, in many, many body problems, these operators exist, but they're hideously complicated. You know, infinite series of terms involving arbitrarily large numbers of electron operators. But actually, in this BCS problem, we get lucky. Because of the very simple form of the BCS state, which I left on the board up there, it turns out that these operators that create the physical excitations of the state are actually just linear combinations of the original electron operators. And I'm just going to prove that by writing such a thing down and showing you that it annihilates the ground state. So here we're lucky. B is linear in C, and somewhat disturbingly perhaps also C dagger. So I'm going to do one with an upspin because the derivation's difficult if you don't assume some direction of the spin, but you can do downspin just as well. So I'm going to say that my true excitation annihilation operator, labeled by momentum K and spin up, is going to be UK, the same UK that appears in the BCS ground state, times CK up, minus VK times C minus K down dagger. Crazy world. Now, this is a slightly odd thing, right? This operator annihilates an electron, this creates one, but if you think that we're starting from a metal, actually, maybe that's not too surprising. So the excitations to annihilate an excitation in the metal above the Fermi surface, I use this. To annihilate an excitation in the metal below the Fermi surface, I use this. Because excitations below the Fermi surface are holes, so they're annihilated by creating electrons. And of course, in a superconductor, I've kind of fuzzed out the distinction between being above the Fermi surface and below the Fermi surface. So it's maybe not surprising that my excitations have some electron components and some hole components. And you can see that deep in the Fermi deep inside the Fermi sea, where the excitations are only holes, the U's vanish, and then this is just the hole annihilation operator. Way above the Fermi level, where the excitations are just electrons, the V's vanish, and this is just the electron annihilation operator. So this is doing the right job when we're far away from the Fermi level. It's just that near the Fermi level, I have to take this phase coherent superposition of electron annihilation and hole annihilation to actually annihilate a physical excitation.
The big excitations are all from this restriction, right?
Yes.
So there can't be anything happening to the Cooper pair as a pair.
That's right. That's right. So what reconfigurations of the Cooper pairs are basically captured in the spatial behavior of delta, at least in most circumstances. So no, that's right. And what we will end up showing is that these excitations, which are single particle-like, actually have an energy gap, which means that if you perturb the system at scales well below the gap scale, you don't see them at all, or you see exponentially few of them.
And that's the spirit of the condensate.
Yeah, exactly. So at low temperatures, the condensation tell you everything that's going on. But obviously, if you make a local probe, that's kind of high momentum. And so you might, if you put the voltage high enough, you'll be able to tunnel into these single particle type excitations as well. Yeah. So let me just show you that this really does annihilate the ground state. I think it's important not to take these things on trust. And it's also instructive to see how it does it. So we can check that the ground state has none of these things. So I act BK up. Soon I'm going to stop writing the hats. So I act BK up on the BCS state. And you can see that because all of the factors in the BCS state are bosonic, right? They either contain 0 operators or 2, they will generally just commute with this unless they snag on this operator or this operator because they also contain it. And there's only one of those factors that contains this or this, and it's the one corresponding to the same K as the excitation I'm trying to annihilate. So really, all the other stuff you come out to the front, and then the real problem is what happens if I get UK CK up minus VK C minus K down dagger acting on UK plus VK C dagger K up C dagger minus K down acting on the fermionic vacuum. So let's just multiply that out and see what we get. We have UK squared times CK up, all of this will act on the vacuum in the end, minus VK squared times C minus K down dagger, CK up dagger, C minus K down dagger, and then the cross terms plus UK VK CK up dagger, no, sorry, CK up dagger, C minus K down dagger, minus UK VK C minus K down dagger, all acting on the true vacuum. And sorry, I shouldn't say equal. We still have this prefactor, but it's not going to do any work. So let's look at what we have. This involves taking the vacuum and trying to annihilate an electron. Can't do that. So this term becomes 0 when it acts on the vacuum state. This term involves double creation of an electron in the same momentum and spin state, and so is 0 by the exclusion principle. Doesn't even matter which state it acts on. This measures the number of holes in the K up state. Acting on the vacuum, that's precisely 1. And so we get UKVK C minus K down dagger minus UKVK C minus K down dagger. And that's exactly 0. So that's how it works. And let's think for a moment about how it worked. So what we've really done is cleverly arranged it so that the part here, which is annihilating one of the electrons in the Cooper pair, exactly cancels the part here, which is creating an electron in the empty bit. And of course, these are phase coherent. So if I have two phase coherent things, destructive interference is a possibility. And I've arranged the amplitudes in my annihilation operator for the true physical excitation in such a way that it will cause these two bits of the superconducting state to destructively interfere. Right? I pull the 2 electron bit down to 1 electron. I pull the 0 electron bit up to 1 electron. They can now interfere because they have the same number of particles. And then I fix the phases so that that interference is perfectly destructive. So that establishes that this operator, or rather family of operators, because I could do this at any k, annihilates an electron, annihilates a true physical excitation of the BCS state. So I can now state the thing the other way around, which is what I wanted. That means that B dagger K sigma, which is defined just as the Hermitian conjugate of this, so UK star C dagger K sigma minus VK star C minus K minus sigma create excitations of the BCS state. And because the BCS state was just a product of fluctuating empty and Cooper pair states at each k, the excitations live at each k as well. Okay. So now we have some candidate operators. We should ask some questions about their properties. So, for example, we should want to know what their statistics are. Maybe not completely obvious from this, although someone said it already. But perhaps more importantly, we should want to know what their energies are. So what's the spectrum of these excitations? Okay, so that's the question we'll move on to for the remainder of our time. Today, that is. Not for all time. Any questions at this point about this construction?
So is it a unique construction?
It's a good question. It turns out that it is. One can show that these exhaust the spectrum of single particle states, and somehow that's done by essentially by counting. Right? So I started off with a system that had 2 excitations at each k point, right? C dagger k up and C dagger k down. These operators have 2 excitations at each k point, B dagger k up and B dagger k down. So I've already used all of the possible linear combinations of the C's and C daggers. Yeah, so it turns out yes, but it's not obvious that it was gated. Other questions? Yeah.
Maybe that's a question, but just because you brought up technique and navel gazing. Maybe one way I've always found it clear to do this is to just solve the variational problem at each k, as you say, breaks up. So you could say the ground state, you variationally can solve the Hamiltonian problem of each k minus state in the 2 particle sector, and you will find, and then the 1 particle sectors.
Okay, sure. Yeah.
So it's just,
Perfectly happy with that.
and also, we do get the counting.
Yeah, okay, which is essentially the argument I've just given, but done K point by K point. Yeah, but completely agree. Yeah.
The momentum of excitations lie in the region which we define for the BCS state, right?
Sorry, say that last bit.
When we define our BCS state, we define the momentum range, right, above the Fermi surface, right?
Yes, okay, but that's actually fine because we defined a momentum range where the attractive interaction happened. But actually a property of our solution was that the superconducting order parameter is non-zero in a much narrower range. And so when we get beyond that range, these revert to the original operators anyway. So when we're further than mod delta over h bar Vf from the Fermi level, this thing goes back to either pure electron creation if we're above the Fermi surface, or pure hole creation if we're below the Fermi surface. So it's actually fine to use this even beyond the original range of the interaction. The state is good right to the center of the Fermi sea.
So can we say that whatever operator acting on psi giving 0, it's an annihilation of an excitation?
Yeah.
Or just in this particular case because we have the Liouville transformation of C?
No, we can quite generically say it. If I have a state that is the ground state of my problem, then any non-Hermitian operator that annihilates that state must therefore have a conjugate that creates an excitation of that state. The difficulty is that principle is not normally very useful because identifying those operators is a matter of art. Often you can identify a few, but sometimes they turn out to be dependent on each other. Right? The early beta ansatz solutions had lots of problems this way. They wrote down lots of excitations of the ground state, but it turned out that some of them were functions of the others. So here, because we're in a very simple situation where there are only 2 excitations per K point, and we know that excitations at 1 K point will commute with excitations at any other, it's quite easy to see that we have a proper, linearly independent, mutually commuting set. And we can show that by checking the algebra of these things, which will also give us the statistics. But the principle applies in general. It's only useful in certain simple problems.
The complete set.
Yeah, exactly. Yeah. Other questions? Excellent. Let's 3 more balls. Oh, yeah.
Sorry, this is from a few minutes ago. When you were talking about the BEC-BCS crossover, is it correct to say that this variational and that will break down in capturing the ground state? As because you have a general gap equation, you don't have to
yes.
solve them properly.
I think the answer is it will. And I think there's an issue because the chemical potential has to cross 0 at some point. The chemical potential is positive for the metal, in fact, it's equal to the Fermi energy for the metal. And then as you turn the interaction up, the chemical potential drops. The chemical potential is strongly negative for the BC, the chemical potential for the original fermions. So I think you get into trouble somewhere where it crosses 0 or near where it crosses 0. And for a long time, there was a suggestion that that point where the chemical potential crosses 0 was an actual transition from the BCS state to the BEC state. But Nozier and Schmidt-Ring argued, I think convincingly, that there's actually no transition there. So a pure S-wave BCS superconductor can smoothly evolve into a BEC of molecules of the constituent fermions without any phase transition needing to happen.
One could write a variational class bigger than this that captures the whole.
I think that's right. And I think that's done to some extent in the sort of post-Nozier-Schmidt-Ring literature on this. Not that I'm a great expert on it. Yeah, but I think this one gets into trouble when you lose the bit below the Fermi level, when the chemical potential goes through 0. Others?
But could you still use this gap equation, for example, if we have competing orders?
No, not this gap equation. So this gap equation is based on a very specific ansatz state, which is designed to have only one type of order, which is superconductivity. Now you might say, well, if I had competing orders, I'd have an order parameter for the superconductor, and I'd have an order parameter for the charge density wave or whatever it is. They should sort of feed back on each other in some way. And you can do analyses that are like that. You can do mean field theory in multiple channels, and then you can get sets of self-consistency equations where the channels feed back on each other. And you could even, I mean, it's the results from that aren't always perfect, but you can do it. I'd say the results from multi-channel mean field theory relative to the truth where we know it are generally less reliable than the results from single-channel mean field theory relative to the truth where we know it, which is why people have developed all these techniques like Parquet renormalization group to try and follow things through from higher temperatures. The basic problem is that if you have only one dominant order, then as you lower the temperature, that susceptibility just grows. And it grows in a way that's well predicted by your high temperature calculation. And then at some point it diverges, and then you have your ordered state. Whereas if you have a superconducting susceptibility growing and, say, a density wave susceptibility growing, as you cool the system, but well before you order, those kind of jockey for position with each other. And so when you have multiple susceptibilities diverging, your high temperature calculation becomes a much worse guide to what's going to win. And the flip side of that is that a zero temperature mean field calculation doesn't notice that the effective couplings have changed on the way down to the ordered phase. So with multi-order problems, you often need more heavy duty kind of RG type methods. And even they're not that great. And I speak as someone who has done some calculations in them and published them, but they're still not that great. Yeah, good question. Are there others? Right, I'm going to try a feat of memory. This is a poem by W.H. Auden, which he wrote when he was very young, and which I do not know that I remember all of. But I'm going to try, because often it comes back to you when you start. It's untitled, in fact, and it's really gothic. Lady, weeping at the crossroads, would you meet your love in the twilight with his greyhounds and his hawk upon his glove? Bribe the birds then in the branches, bribe them to be dumb, stare the hot sun out of heaven that the night may come. Starless are the nights of travel, bleak the winter wind. Run with terror all before you and regret behind. Run until you reach the ocean's everlasting cry. Deep though it may be and bitter, you must drink it dry. Wear out patience in the very chambers of the sea. Search through every sunken shipwreck, find the golden key. Press on to the world's end, bribe the dread guard with a kiss. Cross the rotten bridge that totters over the abyss. There stands the deserted castle, ready to explore. Enter. Climb the marble staircase, open the locked door. Brush the cobwebs from the mirror, doubt and danger past. Something. See yourself at last. Put your hand behind the wainscot, you have done your part. Find the penknife there and plunge it into your false heart.
Well, thank you. I personally feel a lot better now.
Sorry, I was a line short, but we did get to the end. Right. So last question is the energy, or last question for today. And we're working with a variational state. So really, it's not too difficult to work out the energy since we know the operator that creates the excitation. So our excited state is one of these W of quasi-particle creation operators acting on the BCS ground state. And the energy of the excitation is the expectation value of the Hamiltonian in the excited state minus the expectation value of the Hamiltonian in the ground state. And since we know how to write the excited state in terms of the ground state, this is BK sigma Hamiltonian BK sigma dagger. This is just H. And we know BK sigma dagger is UK star CK sigma dagger minus VK star C minus K minus sigma. And so in the end, we just have strings of up to 6 fermionic operators here, strings of up to 4 fermionic operators here. We have an explicit expression for the BCS ground state. We just put these things in, smash them all into each other, and see what we get. I'm not proposing to do that because it's mechanical. But the answer is in some things that we learned about the values of U and V when we did the original minimization, that it is this. And we had already seen this combination cropping up when we did the minimization of the energy to get the ground state. So it's maybe no surprise that it turns up here as well. But there's now a meaning to this thing which appeared in the BCS gap equation, which is that it is the Bogoliubov quasi-particle energy at that K. So how does it look? Well, let's remember that we're in 3D. That's actually really important for something that's about to come next. So if I plot this EK sigma, obviously it doesn't depend on the spin direction because we still have time reversal symmetry. Asymptotically, it goes back to the single electron dispersion, which of course is linearized about the Fermi surface and so appears here as a straight line. But then it rolls over as we get close to the Fermi level, and there is a finite energy gap mod delta to the first of these Bogoliubov quasi-particle excitations. So without doing any further thinking, or it's not much, we can note that this already explains the fact that the specific heat at low temperatures has this activated form. So to put entropy into the system, I have to create some of these Bogoliubov quasi-particles, and I can't really do that until my temperature becomes comparable to the gap scale. So like any other system where you have to overcome an energy gap to insert entropy, it has this activated behavior of the specific heat capacity. The long wavelength excitations of delta itself don't carry entropy. This we discussed a little bit in the context of the superfluid. This is because they're really adjustments of the ground state to the boundary conditions. So when you excite a supercurrent, you've really just altered either the boundary or the initial conditions in such a way that the ground state now carries such a current. That's different from putting a finite number of particles into different single particle states, which the thermal bath can then mess around with and which have some configurational entropy. Now, of course, you could say, well, might there be other types of excitation of the superconducting ground state beyond long wavelength variations in delta and the Bogoliubov quasi-particles? And to that I would answer, no. We haven't proved it, but we can see that it's true, right? Because if there were other things living in this gap that carried entropy, we'd see them here.
Quick question. You have delta as a well-defined scale there, and then there's a sort of asymptotically definable energy scale, which is the scale over which you cease being a Bogusubov quasi-particle and begin to be an ordinary Fermi liquid quasi-particle.
Mhm.
Is that must be of order delta as well, or is it not?
If I remember correctly, and I would have to check this, there is actually no such scale.
Mhm.
Because the U's and V's approach zero like power laws. So I could only define a scale if they were decaying exponentially.
Mhm.
And I mean, in my sketch, maybe they did look exponential, but I don't think they are. I think in this solution, they actually decay to zero on their respective sides of the Fermi level like power laws. And so strictly speaking, that scale is infinite. Others? Okay. So, oh yeah, inertia. Okay.
This makes no sense, but I'll try. Is there any setting in which thermal fluctuations could cause phase differences and thus have you fluctuate between what seems like a long wavelength? So,
Yeah.
like if you had a junction, but can thermal fluctuations
Yeah, I mean,
cause?
yeah, sure. So there are plenty of instances where this neat separation between long wavelength fluctuations and stuff that we're doing on the scale of delta stops working. Granular superconductors, systems made of small islands, Josephson junction arrays. I mean, there you really have to go back and write the theory for the zero-dimensional system. And then, you get whatever separation of scales you get. Here, we're sort of relying on having a coherence length, which is much, much larger than the microscopic lattice spacing effectively, and then saying, well, these things are kind of more or less lattice scale physics going on. And then you have the stuff on the coherence length scale, which is much longer. But short coherence length superconductors, like the cuprates, for example, don't obviously fit into that description neatly. So again, it's a bit of a cartoon, but it's a jumping off point for thinking about what the corrections would look like.
In which case, the activated behaviors go away.
Yeah, that's right. So you'd start to see changes in the lower temperature specific heat that came from, well, intermediate wavelength excitations, I suppose you call them. Yeah.
So you said that the three-dimensionality was important if it's less than that. Can you say a little bit about what would be?
Yeah, so actually my last point is about the three-dimensionality. So for the formation of the superconductor, it's not important, but for what you see in the density of states of these Bogoliu bonds, it's really important. So actually, let me just make that point. This is a gross caricature, but I'm a theorist. So let's do it anyway, and say that tunneling basically just measures the density of states of the single particle excitations. Now, you would be tempted to say, well, look, these excitations have a quadratic band. They're in 3 dimensions. So they should just have the same density of states as free electrons in 3 dimensions, which is square root of energy. So you predict, if you thought that the tunneling would be 0 until you got to the gap scale, and then it would rise like a square root. But that's not what you see, and that's not what the density of states really is either. The actual density of states of these Bogoliu quasi-particles is like this. So there is, of course, the energy gap delta here, but then there's a 1 over square root singularity at that edge, which for reasons that are always slightly mysterious to me, is called the coherence heat. And to understand why that's there, you have to picture properly what's happened in 3 dimensions. Right? The point is, this is actually relative to KF, which people are often careless about drawing. But if I draw the picture of what really happened, I used to have, let me try and draw it in down. So I used to have this, and now I have this. So what the pairing has done is basically folded over the bottom of this free electron dispersion, right, mixing particles and holes, and it's used it to complete the Bogoliubov quasi-particle dispersion. So these are the original electrons. These are the Bogoliubov quasi-particles.
So you put T's on that.
Sorry, that would probably make sense. So this is K. Imagine I'm doing it in one dimension, or maybe it's Kx, right? I'm cutting in some particular direction through the dispersion. So I had a K-squared dispersion with an arbitrary 0 for the original electrons. There's some Fermi level, which I had in the original metal. And then what I've done is made this gap, mod delta, above that Fermi level to excite my first Bogoliubon. And you can think of it basically, I mean, we sort of said that deep in the Fermi sea, these things have the energies of holes. So the hole-like excitations look like the electron ones, but turned upside down. Well above the Fermi level, they have the energies of electrons. And in between, they cross over.
So shouldn't delta be around the Fermi level rather than just above it?
Well, okay. Strictly speaking, I shouldn't be drawing it on this axis, because when I formed the superconductor, I changed the 0 of energy by including a condensation energy.
Yeah.
So really, this is EF for the free electron case, and it's the energy of the BCS ground state for the superconducting case. And I've lined them up, but actually they're not lined up. The BCS ground state energy is less than the metal ground state energy, which is why the superconductor formed in the first place. Yeah. So what you can see is that if I did this in 2 dimensions, I would actually have a ring of points where I have this quadratic minimum. And a ring in 2 dimensions is like a point in 1 dimension. If I'm in 3 dimensions, I have a sphere where a sphere in K-space, where I hit the bottom of this band. A sphere in 3D is like a ring in 2D, which is like a point in 1D, and a point in 1D, where I have a quadratic band minimum, has a square root density of state, has a 1 over square root density of states. So it all comes, this is the literal density of states of those Bogoliubov quasi-particles. But you have to remember that although in people's sketches, they tend to turn up at the origin on the graph, it's actually really important that you can make Bogoliubov quasi-particles anywhere around the Fermi surface. And so that minimum of the dispersion exists on a complete sphere in momentum space. And it's that spherical nature that gives you this extra lump of states.
So how would that look in a 2-dimensional superconductor then?
Well, it would look the same because a ring in 2D is also like a point in 1D.
Okay.
So it's like it sort of catches up. So the dimensionality of the Fermi surface offsets the dimensionality of real space. The dimensionality of the Fermi surface, and therefore of the Bogoliubov dispersion minimum surface, is always 1 less than the spatial dimension.
Okay.
And so if the dimension of the surface where the minimum happens is always 1 less than the spatial dimension, then you always get this.
Okay, but then back to Joe's question about what you were saying about the specialness of 3D. In that sense, it's not special.
No, okay, sorry. So I mean, no, it's not really 3D. It's remembering that this isn't a K equals 0. Yeah. Yeah, good.
Can I add an experimentalist comment?
Please.
This is fantastic, but, you know, over the past 20 years, notably driven by Seamus Davis's group, you can do these things called quasi-particle interference, where you take a dispersion of anything and you realize that it's going to give you a static interference pattern in real space if you can scan your tunnel junction, right? And they can really, you know, their observations are really going as a function of energy through this Bogor-Yubov quasi-particle spectrum. Most of what they're seeing is the quasi-particle interference of Bogor-Yubov quasi-particles in the cuprates, but they can then drive the energy all the way up to see the Bogor-Yubov interference gradually going into standard Fermi liquid interference. I mean, these are remarkable experiments. Totally, that's how I learned about Bogor-Yubov excitations, actually.
and as somebody quipped at one conference in the late 1950s, they agree with the theoretical facts. Good. Any questions on what we've seen today before we shuffle on? Excellent. Well then, thanks very much. Pleasingly interactive. Do keep it up. We'll reconvene 10:30 on Friday, and we're now actually ready to start talking about, you know, what happens if I don't have perfect isotropy, what happens if I don't have a perfectly momentum-independent attraction between the electrons, what other types of superconducting state might I get? Great, see you then.